This is divide and conquer matrix factorization, joint work with Lester and Mike Jordan. So to motivate our work, I'm going to be talking about the problem of matrix completion, which I'm sure many of you guys are familiar with. But the idea here is you're given a subset of the entries of a matrix and you want to recover the missing entries. This problem has been well studied, especially recently, in part due to the Netflix prize and the excitement around that. And oftentimes, to solve these sorts of problems, people make a low-rank assumption. So the idea there is that you assume that a small number of factors are what are needed to determine users' preferences. So for instance, a small number of factors determine what movies people like. So what we're interested in is trying to solve these problems efficiently for very large data sets. So one subset of the algorithms that people have been studying and using recently are those based on the trace norm. And these algorithms solve a convex optimization problem where you minimize the trace norm, as sort of discussed in the last talk. These algorithms have really nice theoretical properties. You can provably show that you recover the low-rank matrix with high probability. They seem to work well in practice as well for small problems, but they don't scale very well. They require a truncated SVD at each iteration, and you really just can't use them for very large problems. So the goal in our work is to come up with a way to speed up these algorithms, keep the nice empirical performance, and also retain the theoretical guarantees associated with it. So we came up with a meta-algorithm called divide, factor, combine. It's a parallel divide and conquer framework, and it involves the use of some base matrix completion algorithm, and then it involves 3 steps. It's very simple. First involves taking the input, dividing it into a bunch of submatrices. Then you solve the matrix completion problem on each of these submatrices in parallel using any base matrix completion algorithm. And finally, you use matrix approximation techniques to combine the estimates that you have from each of the factored submatrices. And this picture below shows 2 different ways we go about dividing and combining, which I'll go over in more detail in the next few slides. But I just want to note here that in this talk and in this work, we focus mostly on algorithms based on the trace norm. That being said, this algorithm works, or should work, for any sort of any base algorithm that performs matrix completion. And in fact, we have tried others other than the trace norm, and at least empirically, we get very similar results. Okay, so the first algorithm, what you do here is you take the full matrix and you sample a subset of the rows and a subset of the columns. And then in the factor step, in parallel, you run the matrix completion algorithm to get to complete the row submatrix and the column submatrix. And finally, in the combined step, we use the generalized Nystrom method, which is a standard technique a standard sampling-based technique to approximate or exactly recover a low-rank matrix using sampling-based methods. And when the matrix you're dealing with is exactly low rank, it is often okay to just sample one subset of the rows and one subset of the columns. However, when you're dealing with a matrix that is full rank or a noisy low rank matrix a noisy low rank matrix, it's often very helpful to employ an ensemble variant of this algorithm. So what we do here simply is pretty much perform the same algorithm multiple times. You can partition the columns and the rows of the matrix, get many approximations, and then just take the average. And in practice, we see that this really helps. The alternative method is based on the projection method. And what we do here is we start with the matrix and we partition the columns into T different partitions. And then in the factor step, we simply, again, in parallel, we run matrix completion on each of these submatrices to get completed submatrices. And then we use the column projection method to combine all of these matrices. And you see the formula there, but essentially what's going on is we are projecting the completed submatrices onto the subspace, the column subspace of one of the submatrices. In this case, we're projecting onto the column space of the first submatrix. And again, in practice, it often is very helpful to, instead of doing this once, do this in an ensemble way, where we project onto each of the submatrices and then average. And I should also note that both in the previous method, based on the Nystrom method, and also this projection method, the time-consuming step is still the factoring step. And even here in the column projection, the column projection requires you to multiply. Let's say this matrix is n by n and very large. It requires n square time at least to do the multiplication. However, since each of our submatrices are factored or returned in factored form by the factor step and their low rank, it's actually much, much faster than without this factored representation. Okay, so first we looked at some simulations to see how this works, and what you see here on the left figure is the performance as a function of number of revealed entries. So as you'd expect, the matrix completion problem is harder as you see less and less entries, or alternatively it's easier as you see more and more entries. So you see all these different curves which correspond to different variants of our dividing factor DFC algorithm compared to the base algorithm that we're using. All the algorithms do better as you sample more and more columns, but what's maybe most notable here is that once you sample 2 or 3% of the columns here, the best of our DFC algorithms, which is the projection ensemble method, pretty much performs as well as the base algorithm. So in terms of performance, there is a trade-off when you sample very, very few numbers of entries. You can do better with the base algorithm than with this divide and conquer method. But just sampling, there's only a very limited window in which you see that issue. And in terms of speed up, we see a really nice speed up here. So the black line on the right, so this is time on the y-axis as a function of matrix size. Again, these are square matrices. And we see the black line is the base algorithm we're using. That should say base MC, not base RMF. And all of the other variants are roughly the same time, because again, the factorization step, we're doing things in parallel. Factorization step is what's really expensive. And we see roughly, instead of, when you have a 10,000 by 10,000 matrix, instead of taking an hour, you take less than 10 minutes. Okay, so then we also have some results for collaborative filtering. There's a fair bit to say in this table, but just to keep things short, the base algorithm we're working with is APG. And so if you leave the square up there, we get an RMSE of 8.8433 and a time of 2,600 seconds. Again, using sampling 10% of the columns of our matrix, using the projection method and using the assembling variant of it, we're able to get the same RMSE and a roughly 10-fold speed up in time, which we were happy about. Okay, and then as I mentioned, we had two goals. One, we wanted to get we wanted to achieve roughly the same performance as the base algorithms, but we also wanted to preserve the theory of these base algorithms. And I don't really have time to go into things too much here, but just to give you an idea of what we had to do to make this work, there were two main steps. The first involved showing that performing matrix completion on each of these subproblems would succeed with high probability, and that involved basically proving that the subsamples that we had the same properties or follow the same assumptions that were made in the original problem. And then second, we had to study the matrix approximation techniques to show that they succeeded with high probability under the same assumptions used by the matrix completion algorithms. And one of the results, we have results for matrix completion in the presence of noise, but just assuming no noise for a second, using the trace norm regularized algorithms, and assuming that you're working with an exact low rank matrix, we show exact recovery with high probability. Of course, nothing's free. We do have a lower success probability, as there's a probability of failure in each of those two steps that I mentioned above. And also, ideally you'd like to be able to sample a small number, you'd like your subsamples to be as small as possible, and we show that the subsample size that is allowable is dependent on matrix size, rank, and the number of entries that you've seen. In the worst case, it can be linear. In the best case, it can be logarithmic in the size, and it's usually somewhere in between in practice. I don't have time to show this video, so I will skip it. But just in summary, so we developed a distributed framework for matrix factorization. When working with trace norm regularized algorithms, we're able to get the same performance roughly and similar theoretical guarantees. And also in the work, we deal, as I said earlier, we deal with noisy settings of matrix completion, and we also deal with another interesting problem called robust factorization, which other people call robust PCA, where you're trying to compose a matrix into a sparse and a low rank matrix. So yeah, we have posters right there, and we'll talk to you about it. Thanks.